This conference will now be recorded.
Hello everyone. So we'll start with chemical properties of alkene. We have already started this topic, chemical properties of alkenes, last class, and we are still continuing it. So here, as you can see, under the heading of addition reactions, there are different types of addition reaction based on what type of reagents you have chosen to add to the CC double bond present in alkene. Now, different types of reagents we have already seen, and we are starting here now with the fourth one, which is addition of hydrogen halide, and the name of the reaction is hydrohalogenation. So it is the net addition of one hydrogen atom and one halogen atom, and ultimately the final product will be alkyl halide. So here if we see the net reaction, that will be addition of one hydrogen atom, one halogen atom to the CC double bond of alkene. Order of reactivity of HX is like this, and that is expected because to break the HI bond, that is easier. The distance between hydrogen and iodine is very large because of the large atomic size of iodine, and gradually the bond strength is increasing from HI to HBr to HCl, and that is the reason we have this type of order. Now we will see example of this. Here you can see the heading, which is addition of HX to symmetrical alkene. Symmetrical alkene means with respect to CC double bond, both sides there will be similar type of groups. At similar groups at each end of C double bond C. Now when we have this type of symmetrical alkene, we will see how the addition will occur and why we have separate heading for it, because depending on whether you have taken symmetrical alkene or unsymmetrical alkene, the reagent, how it will behave, that will differ. When it is symmetrical alkene, there is no such thing, because just take the simple example, which is ethylene. Now in this case, when we add HX, it is simple addition of one pi bond will be broken and there will be carbon hydrogen bond formation, carbon halogen bond formation. So this is, you don't have to decide which side you will take X, which side you will take H. But when it is unsymmetrical, that question arises, because now our reagent itself is not symmetrical. Suppose the reagent is like X2, where it is symmetrical. You are adding two same atom, same halogen atom to CC, the two carbons of CC double bond. But when the reagent itself is not symmetric, you are adding one side H, another side X, then obviously the question of selectivity arises. But for symmetrical alkene, there is no such thing. Another example we will see. So methyl, then CH double bond CH, and both sides we have same groups. So here after addition of HX, we will get product like this. So X, and this is basically, you can also write the previous one as CH3, and this one is CH2Me, because one H is added at this second carbon of CC double. Now the second point, addition of HX to unsymmetrical alkene. Now when this situation arises, now the question that is there is a rule based on which we will ultimately will be able to understand what will be the final product. So when it is unsymmetrical alkene, you will have dissimilar groups at each end of C double bond C, and that is the reason we need this rule, and that is known as Markovnikov's rule. So let's see what is Markovnikov rule. The addition of unsymmetrical reagent such as HX, then we have H2O. H2 is also unsymmetrical, because when you consider water molecule, you are basically adding H and you are adding OH to two different carbon. So this is also unsymmetrical. Then H and OX. Now addition of H2O, addition of HOX we have already seen in last class. And there also we have just mentioned that it is based on Markovnikov's rule. But what is this rule actually? We will discuss it today in detail. So when we have this type of unsymmetrical reagent, not symmetrical reagent like X2, then the addition will occur in such a way that the negative part of the reagent adds on to that carbon atom of double bond which carries lesser number of hydrogen atoms. So here if we take the general example, suppose we have any alkyl group, then RCH double bond CH2. So here number 1 carbon and number 2 carbon, I am just numbering it so that you can easily understand the 2 carbons of CC double bond. So carbon number 1, it is attached to 1 hydrogen, 1 R group. Carbon number 2 is attached to 2 hydrogen. That means it is carrying higher number of hydrogen, 1 is carrying lesser number of hydrogen. And just take the example of HX. It is saying that the hydrogen which is the carbon which is carrying lesser number of hydrogen, the negative part of the reagent will be added there. Now you have to understand what is the negative part of the reagent. When it is water molecule, obviously this is the negative part, because we know that we write like this once you break the HO bond. Then when it is HOX, then oxygen being more electronegative, when you break this bond, it will be H plus and OX minus, right? Sorry. The bond will be broken between O and X, not between H and O, because that bond is easier to break. So this bond will be broken, and as oxygen is more electronegative, negative charge will be over oxygen and positive part over X. So if you take HOCl, it will be HO minus Cl plus. Now the negative part that will be adding towards this carbon, the negative part of the reagent, and the positive part of the reagent that will be adding to the carbon which is carrying higher number of hydrogen. Okay, so now if we take actual example, CH3 CH double bond CH2, and if you are adding, suppose you are adding HCl, what will happen? The carbon which is carrying only one hydrogen atom, the negative part will be attached to this carbon. So Cl is attached here, and the positive part is hydrogen. So hydrogen is attached to the carbon which is carrying higher number of hydrogen. So this is the negative part and this is the positive part. So here we have only one hydrogen, here we have two hydrogen. Now this is the rule, that is the Markovnikov rule. But why this rule we have, that is what is the explanation behind this rule? If we want to understand that, then we first have to write the mechanism, because without mechanism we will not be able to understand what is going on here actually. Why the Markovnikov rule is, according to Markovnikov rule we are getting the product, that answer we have to get only through mechanism, that is possible. So explanation behind Markovnikov's rule, we have to understand the addition of HX to some unsymmetrical alkene. So the first step will be, here we will take, suppose the simplest unsymmetrical alkene that you can take is propene, isn't it? Because more simple than this molecule, which will be unsymmetrical alkene, that you cannot draw. This is the simplest one. So first HX, what is happening here? The negative charge cloud, that is the pi electron cloud, that will be attracted towards the positive side part. Now this positive part will generate the actual electrophile. Now the electrophile is H plus. Electrophile is H plus here. And remember, these reactions are known as electrophilic addition to CC double bond. So CC double bond is a nucleophile here and H is electrophile. So the pi cloud is attracted towards H. HX bond will be broken, negative charge will be over X. So what you will get? You will get H3C, CH. Now the question arises that which carbon will be attached, that is hydrogen will be attached to which carbon. Now I will draw both of them and then we will see which one is more stable. Suppose the hydrogen is attached at the terminal carbon. So here this is the terminal carbon. So if hydrogen is attached at carbon number 2, you will get positive charge at carbon number 1. Similarly, another possibility, I am just giving a plus sign because major minor both products will be there. If hydrogen is added to carbon number 1, now it is CH2, and the terminal carbon which is number 2, that will carry the positive charge. Now out of these two, which one is more stable? Now look at this, this is 2 degree carbocation, but this is 1 degree carbocation. So that is why it will be more stable. Here plus I effect from both sides is present, but here it is present only from one side. So that is why it is more stable. Now the second, this is the step 1 where electrophile is added. Now the second part, what will happen? If you draw the more stable compound, more stable carbocation, which is basically intermediate here, and another carbocation is also there, which is this one. You have in the medium X minus. So this X minus, now it will be added to this carbocation, and finally you will get product H3C, CHX, CH3, H3C, CH2, CH2X. Now look at this. We have already seen that this will give you major product, and this one is, so this is the major product where finally X minus is attached to the carbocation, and this will be minor product. Now look at this major product. Here the negative part is attached to that carbon which is carrying lesser number of hydrogen. Now you know what is the actual reason behind this Markovnikov rule. Fine. It is we are getting this as major product because it is from that intermediate carbocation which is more stable. So this carbocation being more stable, it is giving us the major product. Fine. So this is one aspect of addition of HX, that is hydrohalogenation to CC double bond. So this part is fine. When you have unsymmetrical alkene, you just have to follow Markovnikov rule. But don't just blindly follow Markovnikov rule, because sometimes there may be some special type of substrate where you will see, though this is 2-degree carbocation, it is more stable, but it may be that instead of this type of methyl group or alkyl group, if you have some highly electron withdrawing group, then it will destabilize this carbocation. So I will suggest, instead of blindly following the Markovnikov rule, always try to understand the mechanism, because if you know the logic behind it, suppose there is a special type of substrate where there is some electron withdrawing group present that is directly attached to this carbocation. So in that case, this 2-degree carbocation will not stable. In that case, maybe this carbocation will be more stable, because now the electron withdrawing group is far from this C+. Okay, so substrate to substrate it may vary, but in general, when you have this type of normal substrate where electron withdrawing group, or normal substrate means just alkyl groups are there, nothing any special type of different types of groups, then you can follow Markovnikov rule. Okay, so this part is done. Next thing is, if there is a rearrangement, then you will get some different types of product. Now why I am talking about rearrangement? We have not seen rearrangement in other addition reaction. Now the question of rearrangement arises because the intermediate is carbocation, that we have just seen in the first step of this mechanism. You have seen it, that carbocation is involved. Now when carbocation is involved, the question of rearrangement obviously arises. Now in this carbocation that we have just seen, here rearrangement not required, because it is already 2-degree, and even if you do some rearrangement, it is not that you will get more stable carbocation than this. Suppose you are thinking that to shift one hydride from the terminal CH3 group, but if you do so, what you will get after hydride shifting from CH3 part to this middle CH plus, you will get positive charge at the terminal position, but that will generate 1-degree carbocation. So rearrangement will occur only when after rearrangement you are getting more stable carbocation. That is the driving force for rearrangement. But if that situation doesn't arise, no question of rearrangement. So we will see addition of HX involving rearrangement. So we will take a substrate where this type of rearrangement is possible. So what substrate we will take? Look at this substrate. Here suppose we are treating it with HBr. Now when we are treating it with HBr, first of all we will see what are the carbocation possible here. So here I am writing for simplicity Me2C, which is this middle left hand side part, then CH, then CH2, CH2. Now suppose I have added this H to the middle, that is this carbon. If the hydrogen is attached to this carbon, you will get positive charge at the terminal position. But this is 1 degree, it is not so stable. And another possibility is Me2C, CH, positive charge, CH3. So that in the second carbocation, I have added H to this terminal carbon CH2, and that is why you are getting positive charge here. Now this is 1 degree, fine. This is 2 degree. So 2 degree we will focus. But look at this 2 degree. In this 2 degree also some rearrangement is possible, because of which you can get more stable carbocation. Sorry, this is Me2CH, not. Now, what type of rearrangement will happen here? To understand that, this H I will write in a different way. So instead of writing H like this, I will write it in this way. Now, why I am doing so? Because this hydrogen will be shifting to this carbocation in the form of hydride. Hydride means hydrogen carrying negative charge. When hydrogen is carrying positive charge, we call it proton. When it is carrying negative charge, we call it hydride. Now, why this H is shifting? First of all, this carbon-hydrogen bond is broken. H is taking both the electron with it and it is moving towards CH+. Why it is happening? Because if it happens, now look at this molecule, you will get this type of carbocation, which is newly generated carbocation. And here this CH, it is now CH2 and then CH3. Now look at this carbocation. It is getting plus I effect from 3 sides. So this is 3 degree. So rearrangement is occurring because the driving force is after rearrangement, you are getting more stable carbocation. And that is the reason you will get this carbocation as intermediate, which will be measured. And finally, if you attached with it the other part of the reagent, the final product we will get. So this will be our major product after hydride shift. So this is major product, and from 2 degree carbocation you will get minor product, which is Me2CH, CHBr, CH3. You can also consider this one, but that will be very, very minor. I'm just focusing on the after the major, the next minor is this one. So sometimes you may get question that from this type of CC alkene, how many different types of products possible? Then just check whether there is any rearrangement possible or not. It is not that every time rearrangement is possible. Sometimes it may be possible, and only when it is giving you more stable carbocation. Here we have shifted H minus, but sometimes it may be that you have to shift some methyl groups. Not necessarily it is always H. But in this case, we are not shifting methyl groups, because if you shift methyl group to this carbon, the newly generated carbocation, this methyl now it will be H. So it is not 3 degree. So that is why we are shifting H minus, so that you get 3 degree carbocation. Okay. Now another thing that we have to know under this reaction, which is still we are continuing with addition of HX to CC double bond of alkene, anti-Markovnikov addition. So you have already seen what is Markovnikov addition. Now it is saying that anti-Markovnikov addition. So obviously from the term it is clear. Now the rule will be reverse. And this type of effect is also known as peroxide effect or Kharas effect. And why we call it peroxide effect? Because now it occurs in presence of some peroxide bond containing reagent. Peroxide bond means this type of bond that will be present in some reagent. Mostly the examples you will see it is with benzoyl peroxide. So here the mechanism that we are going to see, that will be based on benzoyl peroxide. So in the presence of peroxide compounds, for example benzoyl peroxide, the addition of HBr, now it is only for HBr. Don't think that anti-Markovnikov is applicable for all the HX. No, it is only for HBr. So that is why specifically HBr is mentioned here. Addition of HBr to unsymmetrical alkene such as propene, MECH double bond CH2 takes place in contrary to Markovnikov rule. Now, in contrary to Markovnikov rule means what? Normally, we know when we have propene, in absence of peroxide, that is normal HBr you are adding, the negative part will be added to this carbon, and that you can see here. That is the expected product. But when you have peroxide, now negative part is added to the terminal carbon. Now, this is the difference when you take peroxide and when you do not take peroxide. Another example, this is also unsymmetrical alkene. In the left hand side carbon you have two methyl groups, right hand side carbon you have two hydrogen. And when you have any do not have any peroxide, that is O linkage, you are getting normal product where Br will be attacking this carbon. But when it is in presence of peroxide, Br, which is the negative part of the reagent, it is added to that carbon which is carrying higher number of hydrogen. And that is actually the peroxide effect, which is clear from these two examples. Now, what happens when you have peroxide? First, we will see step number 1. So, in step 1, okay, let me say one thing, that when you have benzoyl peroxide and you are doing this reaction, the mechanism will be based on radical mechanism. So, benzoyl peroxide is this molecule, PHCO. So, OO linkage must be present. Now, this compound, first of all, it will undergo homolysis at this position. As a result, you will get some radical which will be over oxygen, and two of this radical you will get. Now, this radical, from this radical, if look at this PHC, PH means benzene ring. If these two electrons that is present in this CC bond, one electron from this side and this electron together, if it makes a double bond here, that means now you are removing CO2. Two CO2 obviously, because we have two of this radical. So when CO2 is removed, you will get 2 pH dot. Okay. So this is the first step, generation of the first radical. Now this pH dot, it will be reacting with HBr and it will take H in the form of dot and it will be converted to PHH. PHH is nothing but benzene ring, right? So pH dot is benzene ring and one of the hydrogen is not present and there is some dot. When it is already attached to H, it is simply benzene and Br minus. So this is the second step. Now the third step, the substrate will now be present. So here I am drawing the substrate as RCHCH2, which is general. So try to understand the mechanism when you do not have any peroxide. So when there is no presence of peroxide, what happens? Remember the mechanism that we have seen in the previous slide? Just have a look. Here we have seen the first step is the H of HX is added to CC double bond. In the second step, X is added, but now it is something different. Now what is happening? Br dot is attached to this CC dot, one of these CC bond first. After that, H will be attached. So this Br dot, what it will do? Two possibilities are there. Suppose Br dot, if it is attached to the first carbon of CC double bond, then radical will be in the second carbon. Another possibility is RCH. Now Br is attached to the terminal CH2. Now you can understand among these two which radical is more stable. Obviously this one will be more stable, right? Because here you have this C dot which is not primary, it is secondary. Both sides you have carbon. Now from this, what will happen in the next step, that is the final step. Suppose this is A and this is B. So if you have A, which is basically minor, in presence of HBr, it will capture H. And once it is capturing H dot, it will produce RCH3. And there will be generation of Br dot, which can further start another reaction. And if it is B in presence of HBr, B is more stable. Remember, RCH2, CH2Br. Now this one is more that is from B, which is more stable. B is more stable than A. You are getting this one, and that is the reason now it will be measured. And look at this. This is anti-Marconic of addition. Br is attached to that carbon, which is just look at the initial substrate. Br is attached to this carbon, which is carrying higher number of hydrogen, and this is reverse of Marconic of 2. So the reason is it is undergoing radical mechanism, where the first step is that is first the Br part of the reagent is added, and here the question of negative part, positive part doesn't arise because it is radical. It is not carrying any negative charge, right? So this is the mechanism in presence of peroxide. So mechanism of peroxide we have already seen, but here one point, as we have already mentioned in the previous slide, that this is only applicable for HBr. But why it is only applicable for HBr? Suppose you are doing the reaction in presence with HI or HCl, and you also have peroxide. Then anti-Marconic of addition will not take place. Only for HBr, the question of anti-Marconic of addition arises. And the reason is anti-Marconic of addition occurs only with HBr, not with HCl or HI, because only in case of HBr, both step 3 and step 4 are exothermic. So remember what is step 3? Step 3, what is happening? RCH double bond CH2. There is suppose X dot. This X dot is, it may be Br dot, it may be Cl dot, it may be I dot. You are getting CH2X. So you are getting 2 degree. This radical is more stable. So that is why I have written only this one. The other radical I am not drawing. And the second step, what will happen? These are CH dot CH2X. It will take H from another HX molecule. HX means it may be HB or HI, anything. So this is the third step and this is the fourth step. So this third step and fourth step, it is observed that only when you have taken HBr, both the steps are exothermic in nature and it will be facilitated. But when it is HCl or HI, one of these two steps is endothermic. Look at this. This is step 3, where X dot is attached to, this is a propene, which is just like RCH double bond CH2, here R group is methyl, but whatever. You are getting this type of second degree carbon radical. Now HX, X in HX, when it is Cl, that means it is HCl that you have taken. This step is in exothermic, but the fourth step, which is the radical over carbon, it is now capturing H dot from HX, leaving behind X dot. This step is endothermic. When you have taken Br, that is you have taken HBr, both the steps are exothermic. When you have taken HI, that means X is iodine, this step is endothermic, only the step 4 is exo. So in case of Cl, this is exo, but in Br, both the steps are exo, and that is the reason anti-Marconic of addition occurs only with HBr. Okay. The next addition after this is complete, that is addition of HX. The next addition is addition of H2SO4. Now H2SO4, if you draw the molecule, this is H2SO4. But this molecule, if you separate it, suppose this is one part, this is another part, H plus, and another side you have HSO4 minus. Now when you are dividing it in two parts and you are treating it with alkene, see, alkene react with cold concentrated sulfuric acid. This reaction is done under this condition. It must be cold and concentrated. and there should not be any aqueous thing, that is the concentrated sulfuric acid we have taken. We have not taken any water, because if you take water, something else will happen. We want this HSO4 unit to be attached, not the any other part. And that is possible when you have taken cold and concentrated sulfuric acid. And what is formed as product? Alkyl hydrogen sulfate. And that is also in accordance with Markovnikov rule. Only when obviously it is unsymmetrical alkene. And the question of Markovnikov rule obviously will arise, because now your reagent, the two parts, one part is H, another part is HSO3, HSO4 minus. So two different parts, positive part, negative part is present, and you are using some unsymmetrical alkene. Obviously the question of Markovnikov rule arises. So here if we take any general alkene, suppose, and you are treating it with H2SO4, then one carbon there will be addition of H, and another carbon there will be addition of O, SO2, OH. This is the net addition to this CC double bond. Now further hydrolysis of the alkyl hydrogen sulfate. This is this alkyl hydrogen sulfate product is this one. Now suppose your purpose is not to produce this product, but you want to convert this unit. You want to convert this unit to OH group. Then you can use H2O. You have to do some hydrolysis, and finally the product you will get, that will be alcohol. Now you can think that this is addition of net addition of water molecule, right? Which we can directly do. But sometimes if we do it in this way, that is bypassing this another product by using cold concentrated H2SO4, and then we are using water. So this is another way to produce alcohol, which is not direct, it is indirect, right? You can also look at this mechanism, which will help you to understand. So the first step is, this is H2SO4 molecule, it is written in this way. The pi electron cloud will be attracted to this positive part. Del plus sign is there, which means partial positive charge, because we have not broken this bond fully. This is step 1. Now negative charge will be over this oxygen, and this part is HSO4 unit. Now this negative charge it is attacking here, which is step 2. So this product you can say it is alkyl hydrogen sulfate product, but if you are further doing some hydrolysis, you will get H3C one side, and this part will be converted to OH. So this is, you can say, it is overall two-step conversion of an alkene, first into alkyl hydrogen sulfate, followed by hydrolysis with boiling water, ultimately forming alcohol. And this method is indirect hydration of alcohol. Why indirect? Because we are not directly adding water. First we have formed alkyl hydrogen sulfate, and then we are doing some boiling water hydrolysis. Okay, so this is indirect hydration of alcohols. Addition of water. Now you will see this is direct addition of H and OH. Normally water does not react with alkenes. That is, if you take simple water, then there is no reaction, because water itself is not very reactive. But suppose you have taken some water in presence of concentrated sulfuric acid. Now alkene can react with water to form alcohol. Here you can see this is the general alkene structure, and we have taken water in blue color, and net addition of H and OH to CC double bond. And here H2SO4 is not mentioned, but it is written as catalytic H3O plus, because when there is H plus is present in the medium and there is H2O, together it will produce hydronium ion. So that is why it is written in this way. And if it is unsymmetrical alkene, it will be according to Markovnikov's rule, because here also the mechanism is carbocation mechanism. Net addition of HOH, and if we take one unsymmetrical molecule so that we can see the mechanism how the carbocation is generated. So let's take propene, and first in presence of H3O plus. So this is hydronium ion. Oxygen is having some positive charge. This negative charge will be attracted to H. So this is actually the addition of this H plus. You can say electrophilic addition. And you are getting positive charge at this carbon. This is one carbocation formation possible, another carbocation formation possible if you are adding the hydrogen from H3O plus in the middle carbon, that is the first carbon of CC double bond. In this case, the terminal carbon is positive. Now this is obviously more stable than the other, and as it is more stable, obviously, okay, this step is actually in equilibrium also. The next step is also in equilibrium. Now water molecule is present. Take some normal neutral molecule. It will attack this positively charged carbocation. I am showing the mechanism with the more stable carbocation. Now oxygen is positively charged, and in the final step, if we consider another water molecule, this neutral water molecule, it can capture H, and finally you are getting H3C, CH, OH, CH3, and the fate of this H2O is it will produce another hydronium ion, and this can start reaction with another alkene molecule. Okay. So as it is under the mechanism, from the mechanism you can understand that some carbocation intermediate is involved, then obviously the question of rearrangement, it is still there. So if there is a chance of rearrangement, depending on the substrate, that is possible. So rearrangement of carbocation is possible depending on what type of structure you have taken for the alkene. So here we have a question. CH3, CH2, CH2Cl. So this is alkyl halide, right? We are treating it with potassium hydroxide. And look at this solvent. It is not water, it is ethanol. So that is very important, whether you have taken ethanol as solvent or you have taken water. Because if it is aqueous medium, what happens? This Cl is simply replaced by OH. Some substitution reaction occurs. But when it is KOH you have taken in ethanol or methanol, now you will get some elimination product, because now this HO minus, it will behave as base, not nucleophile. If it is behaving as nucleophile, it will simply replace the chlorine and that place will be taken by OH. You will get some alcohol, but that is not the case here. This carbon is alpha, this carbon is beta, and this hydrogen will be removed along with Cl. So ultimately you will get CC double bond. So from beta position, so this was the original beta position, this is original alpha position, and in this position now you are getting double bond, because HO minus first will capture this H, CH bond will be broken, then Cl will also be removed. So this is a mechanism of elimination that we have already seen in that heading, under the heading of how to prepare alkene, starting from alkyl halide. There we have seen this reaction, right? So this is molecule A. Now if it is A, next you are adding HBr, and this reaction we have seen in today's class. So it will be according to Markovnikov's rule, because your reagent is unsymmetrical, your alkene is also unsymmetrical, and this is the negative part of the reagent, which will be added to that carbon which is having lesser number of hydrogen. Now this carbon is having lesser number of hydrogen, and that is the reason Br will be attached here, and hydrogen will be attached here. So this is CH3, CHBr, CH3. Fine. So this is identify A and B in the above reaction. This will be our A and B. Next question. Identify A and B respectively in the following reaction. So again, we have to identify A and B, but now we have some options, but structure is not given. Some nomenclature is given. So this nomenclature, it is repeated 2 times, 2-methyl propene, 2-methyl propane. Then in C and D, you have 2-methyl propane, and again same. So these two alkene, but C and D, the first compound, that is A, that is alkane. Look at the reagent. Substrate is alcohol. Look at the reagent. It is 20% H2SO4, 363 Kelvin. 20% H2SO4, 363 Kelvin. We are getting A along with H2O. Now this is very important information. You have started from some alcohol. You are treating it with H2SO4 and you are getting some molecule plus H2O. That means from alcohol water is removed. This is simply dehydration reaction. And when there is dehydration reaction from alcohol, you get alkene molecule, isn't it? So here we will draw the molecule tertiary butyl alcohol. This is tertiary butyl alcohol. Tertiary butyl group, and you are having some OH group. Now the first, in presence of the first reagent, there will be removal of water molecule. So this is dehydration. And here the type of, that is OH will obviously be removed, and H will also be removed from the beta position, and all the beta position you have similar type of that is identical positions. So no question of selectivity. Any of this hydrogen you can remove, and this reaction undergoes that is mechanism is through carbocation. First OH is protonated because H2SO4 is there, and once the OH is removed, you get some positive charge, and then there is removal of H plus. But mechanism not required. We will directly draw the molecule H3C. So suppose I am generating CC double bond here. This is the first molecule. And you can easily cancel these two because it will be alkene. It cannot be alkane. Already water is removed. And how it can be alkane? This part is very important, this information. So A and B, either A or B, but to choose any one of these, we have to consider the second. Now this is 2-methyl propene, isn't it? Because if you are numbering it, this is 1 carbon, this is 2 carbon, sorry, not. Parent chain, we have to do the numbering. So at 2 position you have methyl group, so that is it is 2-methyl propene. Now you are treating it with HBr, and there is also presence of H2O2. That means you are using some peroxide. This is also peroxide. So what will happen? Normally what we know, the carbon with which lesser number of hydrogen is attached, negative part is attached there. So according to Markovnikov, Br should be attached to this carbon, but it is anti-Markovnikov because H2O2 is there and you are using reagent HBr. So what will happen? H3C, H will be added here and Br will be added here. Okay. And it is mentioned as 1-bromo 2-methyl propane. Now it is propane. There is no problem in that. But is it 1-bromo or 2-bromo? So numbering will start from here 1, 2, and then 3. So here you have methyl substitution at 2 position, and at 1 position you have bromo. So it is 1-bromo 2-methyl propane. Not the option B, but option A should be the correct option, right? The reaction of C6H5CH double bond CH3 with HBr produces option A, then option B, C and D. Now C6H5 is what? PH, CH double bond CH3, and you are treating it with HBr. Now you may think that both sides we have substituted, then and we have same number of hydrogen attached to carbon. Then on the basis of Markovnikov, what should we do? Now, even if that is directly Markovnikov rule, if you cannot apply, it's fine. Just see what are the different possibilities for carbocation. So if you are attaching first the H, to carbon number 1, you will get positive charge here. So this is one possibility. Another possibility is if you are attaching the carbon to carbon number, you are attaching the hydrogen of HBr to carbon number 2. Now it is CH2CH3. So this is another carbocation you are getting. Now here you have methyl group which is having some plus I effect, fine. Here we have pH, and remember in pH resonance is possible. Basically if you draw the full ring, the molecule is like this. It is true methyl can also stabilize, but the stabilization that you will get here because of this type of resonance with the CC double bonds of benzene ring, that is far that will give more stability than the methyl groups plus I effect, and that is the reason. Now you have to consider this carbocation from which you will get your final product. So finally what will happen? Br minus will be attached to this carbon. So it should be pH CHBr. So here among all the options, this you can easily cancel. Why? Because the product will be the addition of HBr. The product cannot contain any CC double bond. Now options A, C and D. This will be the correct option. This one. Right? pH CHBr CH2 CH3. In option A, it is attached to the terminal carbon as if the positive charge is here. But that is absolutely not possible. Another possibility is if you consider option D, but C is better because that product you are getting from more stable carbon. So option C, correct option. The major product formed in the reaction is, this is unsymmetrical alkane because one side you have one hydrogen and one CF3 group. It is CF3, it is not CH3. Another side you have two hydrogen. Now if you simply follow Markovnikov rule, what you do? You think that carbon number 1 and carbon number 2, among these two, carbon number 1 is attached to lesser number of hydrogen. So you should attach the negative part of the reagent here, and this should be the correct product. And accordingly, you will choose option A as the correct option. But this is wrong, though it is following Markovnikov rule. So I have already said during the discussion of Markovnikov addition, don't just follow it blindly. In some cases, even if you follow it, you may get wrong result. Because see, here if you consider the two carbocation possibility, the one carbocation that will generate is this one. Now if you consider this carbocation, you get this product, right? But there is another possibility for carbocation, which is this one. If you consider this as more stable carbocation, then your product will be CF3, CH2, CH2, Cl. And that is actually the major product, not this one. Now why? Because here, because of this electron withdrawing group, this carbocation will be very unstable. But though it is 2 degree, but still it is electron withdrawing group. But here CF3 group is far from this carbocation. So though it is 1 degree, but still it will give you more stable. That is a major product. So here option B, CF3, CH2, CH2, Cl, this should be the correct option. So this option you can easily cancel because your product will be some alkane. And option A we are cancelling because it is not according to Markovnikov. Option B we are choosing as correct option. And look at the last option. The problem here is here CF3 group is not present. Here what they have done, as if the product is like this, CH2F, and this side CF2Cl, as if CF bond is replaced by Cl, but that is absolutely nothing to do with this reaction. So this is not correct. Option B will be the correct option. So be very careful about the substrate before you apply Markovnikov. Just check which carbocation is more stable. It will always give you correct result. Here we have alkene and this is cis, right? And it is asking you are doing halogenation reaction because you are adding bromine in presence of CCl4. Remember, solvent is very important because if you do the same reaction in presence of water, then we have addition of HO and Br. But you are doing this reaction in presence of CCl4. So here addition will be of 2 bromine atoms. Now it is asking in the product B the total number of stereoisomers possible for this product. Remember, in the last class, we have seen in detail starting from Z-alkene and E-alkene, or you can say cis-alkene and trans-alkene, and you are doing this reaction, which is undergoing some anti-addition mechanism because it is through cyclic halonium ion or bromonium ion, and anti-addition occurs. And when there is anti-addition, your starting material is having similar groups on same side, that is starting material is cis, then you get mixture of enantiomer. But if your starting material is already anti and then you are doing some anti mechanism, so it will cancel each other and ultimately you will get some meso product. But here it is not meso. Remember the same picture we have already seen in last class, the same picture I have again here mentioned. Different solvent, but doesn't matter, same product, CH2Cl2 CCl4, same thing. So here these two products you will get, and if you see, you will have some mirror image relationship. So if one is 2s 3s, another will be 2r 3r. So these positions are basically 2 and 3. Okay. So in this way, the answer will be 2 isomers maximum possible. Total number of alkyl bromides, including stereoisomers, formed in the reaction. Here, what we will do, we will draw the mechanism. Here we have Me3CCHCH2. Now, one carbocation possibility is this is one possibility, right? Now you can draw another possibility where the positive charge will be at the terminal carbon, that is at this carbon, but that I am not drawing because that will be very, very unstable. But here rearrangement is possible. So if you consider rearrangement, what you will get, one of the methyl group that may be shifting here. And once it is shifted, now it will be carrying positive charge in this carbon, CH3. So from this, finally, when you add bromine, you will get product like this, CHMe2. But if you consider this one, that is before rearrangement, if you consider it, Me3C, CHBr, CH3. So another isomer we have not considered because that is very unstable. So from this, the product that you are getting, it is mentioned including stereoisomer. So you just have to check, is it chiral or not? Now this carbon is chiral because all the 4 groups are different, isn't it? But the second carbo product, which we are getting after rearrangement, that is basically not chiral. Here you will not find any chiral group because if you consider this carbon, 2 same groups there, this carbon is also 2 same methyl groups. So this is not chiral. So from this you will get total 2 enantiomer, and from this you will get 1. So 2 plus 1 you will get 3, and that is actually the maximum number present in the options. Because even if you consider the another carbocation, which is basically this one, even if you consider this carbocation and you write the corresponding product, then you may think it will be 4, but that option is not here. So you can simply cancel this carbocation from which you have made it because it is very unstable. So ignoring it, this will be the correct option, right? The major product A of the following given reaction. So this is the given reaction. Now the major product A that you will get in this reaction, in that product has dash sp2 hybridized carbon atom. So first you have to draw the major product A, its structure you have to draw, and then you have to check how many sp2 hybridized carbon atoms are there. Fine. So you will first draw this molecule 2,7-dimethyl 2,6-octadiene. So here what we will do, 1, 2, 3, 4, 5, 6, 7, 8. So we have drawn the parent chain, which is octadiene. That means oct is the total number of carbon is 8. So this way, stepwise, you have to think. Now at 2 position, you have a methyl group. At 7 position, you have a methyl group. Look at the diene position. You have double bond at 2 position. You have double bond at 6 position. So these are the positions of the double bonds. You are adding now H plus. Now this is a symmetrical molecule, and any of these CC double bond can be attacked by H plus. So first, suppose I am that is this CC double bond, it is attracted to this H plus because no other reagent is there, simply H plus. There will be generation of carbocation. Now two types of possibilities are there for carbocation generation. If the H is attached to carbon number 7, positive charge will be carbon on carbon number 6. And if it is hydrogen is attached to this carbon number 6, then you will get positive charge at this 7 position. And that will be more stable because it will be 3 degree. So if we draw it, this double bond is intact. Hydrogen is attached to this carbon number 6 and we are getting positive charge here. Now what will happen, because we do not have any other reagent, the next thing that is going to be occurring is attacked by the CC double bond which is already present in the molecule. So it is intramolecular attack, intra, that is within molecule, as if this part it is acting as nucleophile and this pi bond electron cloud will be attacking this positive charge. As a result, you will get some ring type of structure. So I will do another fresh numbering, and that numbering is not according to this 2,7. This numbering I am doing because based on this numbering, it will be easier for us to draw the final ring structure. So suppose I am drawing it as 1, 2, 3, 4, 5, 6. So why am I putting numbers like this? Because carbon number 1, this electron cloud from 1, it will be attached to 6. So basically, you will get some 6-membered ring. Okay. Now you can think that why not carbon number 2 is attached to 6. But in that case, you will get some 5-membered ring. Here we will give more preference to 6-membered ring because of stability. So that is why we have drawn 6-membered ring. Now as it is 6-membered ring, let me draw the numbers so that it will be easier for us to put the substituents. 4, 3, 2, 1. So 6 and 1 carbon, these two are now connected. And look at 1 carbon. At 1 carbon, there is 2 methyl groups. And at 6 position also, there is 2 methyl groups. But as this double bond is shifted from towards 1 carbon, negative charge is accumulated on 1 carbon. So 2 must be deficient. So this is your positive charge. Now, if this is the positive charge, you have to see whether rearrangement is possible or not. Because this carbocation is 2 degree, and if this side methyl group is shifted here, you will get a new carbocation which is more stable than this carbocation. So now at 2 position you have this methyl group, and the original 1 position you have 1 methyl, but you also have a positive charge. Now this positive charge is 3 degree. So from 2 degree you are making 3 degree by methyl shifting. So finally from this one hydrogen will be removed. Here we have hydrogen. So this CH bond will be broken. It will make CH double bond. So this is CH double bond. Methyl groups are there. At 2 position methyl group, at 3 position, 1 position, 1. We have 1 methyl. But how many sp2 hybridized carbon? That is the question. So it is only 2. Only 2 sp2 hybridized carbon are there. So that is why the answer will be 2. Total 2 sp2 hybridized carbon atoms are present. Okay. Now this question will not be able to start because that will take much time. So we will close the session here. Thank you for your time.